Okay, so in this video, we're going to talk about another parametric curve called a hypocycloid. Okay, so this is a little bit more complicated to derive, but it's derived basically the same way or very similar to the way we described or derived the cycloid. Okay, so let's start with the first piece of this. Okay, so the first piece is what's going on with the center. Again, we're going to figure out what's going on, how is the center behaving as it moves, and how is the point along the edge of the smaller circle behaving. So in this hypercycloid, what we have, or hypo I should say, in a hypocycloid, we have a larger circle, okay, and we have the smaller circle in blue that is rolling along the inside edge of the larger circle. That's the setup, okay? So visualize a wheel of some sort or a circle just rolling along without slipping on the inside of the larger circle. Let's say a couple of gears, if you will. You could feel like a gear moving along the inside of another gear, okay? And again, if you've ever bought one of those, what they're called spiral graphs, like the you buy for your kids, and it has all these different circles, and it has one large circle with all these gears on the outside and the inside. So you could take one of the smaller ones with your pencil, and you put it on the inside, and you can, with your pencil in one of the holes, and you just go along the inside, you trace, and you just follow the pencil. This is exactly what we're doing here on the board here, but that's what they're actually doing. They're making hyper and hypocycloids. And again, depending on which hole you put it in and how big the center is, tells you what kind of shape you're going to have. Okay, so let's just look at this. So the first thing is, let's focus on the center. How is the center moving, right? So again, the center is moving along a constant path, okay, around the inside of the circle. So to describe the motion in this case, what do we have? It's going to trace the orange path, right? So it's going to be another circle, right? So we can look at the distance, right, from the origin, right? So our reference is going to be the origin. So how can we describe the position of the center of the smaller circle with respect to the origin now? Okay? Well, we can look at it as an angle, right? So we can have this angle T, right? And so we can represent this as what? An X and a Y coordinate. And so it's going to be constant too, right? Because it's going to have a constant radius. So what's the radius of this inside circle, the orange circle? Well, it's going to be the radius of the larger circle, A, minus the radius of the smaller circle, B, right? Because this is going to be this radius minus the radius of the smaller circle, which is B. So the radius of the inner circle is going to be A minus B. Okay, so let's set that up. Okay, so the radius of the orange circle is A minus B. That's the radius. Okay, so now we know the radius. Now how can we write the component vectors, if you will, the component sides of the right triangle? Well, we would write X is equal to what? It's going to be opposite, it's going to be adjacent over hypotenuse. Well, we know this is the radius, which is the hypotenuse of the right triangle. So we could say this is going to be the adjacent side, right? Divided by, so cosine t is the adjacent side divided by the hypotenuse. So that would mean that we could write X is equal to A minus B, right, times cosine t. Okay? And similarly, we can write y. So since this is just constant, so we could say this is going to be x of t then, right? There's our parametric equation that describes the pathway of the center. So let's put that down here. So this is all based on about the center. And then of course we could describe the y-coordinate as a function of t, and that would also be similar, which would be a minus b sine t. So these two coordinates will describe the location of the point anywhere along the orange circle. Okay? So that describes the path of the center. Now, what about the point on the edge? As it's rolling around the inside of the circle, it's also moving and rotating around the center. So how would we describe the location of this point with respect to the origin? Because it's going in and out, right? So, well, it turns out it's going to be a multiple, it's going to be a proportion of t, okay? So I'm not going to derive it, but notice that depending on where this is at along the circle, the blue circle, okay, I can always represent this this here with respect to the center, right? So I can draw a small rectangle here, and I can do the same sort of thing I did before in the with the respect to the cycloid. So I've got a small triangle in here, and so what's the distance here? And what's the distance here? Okay, well, the x-coordinate, so let me just, I'll say point on the edge. So point on edge. So if I want to represent the x distance, right? So the x distance, x of t, well, depending on the angle, t, right? So, if I draw and it's hard to see here, but if I draw another triangle going this way, so if I draw, so I've got my blue triangle, the little triangle, but if I draw another triangle going all the way down, I've got another right triangle here, right? And so what I'm going to have is two similar triangles. And remember, the one thing about similar triangles is that they are proportional, right? Corresponding sides are proportional. So this angle is the same as this angle because I've got a transversal that's intersecting two parallel lines, okay? So if I take this is going to be proportional to this side, okay? And this is going to be proportional to this side. And so if I take those into consideration, what I end up with is I get x of t is going to equal what? It's going to be a minus b divided by b. So I'm going to get b, now let me see here. Okay, so let me back up. So the angle is going to be, for example, cosine, again, divided by b, right? Because again, this distance is b. So the hypotenuse is b. But what is this going to be? This is going to be proportional to the larger triangle. Okay? So, what do we end up getting? We end up getting let me write it this way. We get cosine of what? Well, the angle is going to be A minus B divided by B times T. Okay, and that's going to equal adjacent over hypotenuse, which in this case, the adjacent what's the adjacent going to be? X over B. Yep. So that's going to be X over B. Because again, this represents X, right? The distance X from here to here. Okay, divided by B, okay? But because these are proportional, we're taking a proportion of that, okay? So what this gives us is X of T is going to equal B times cosine of A minus B over B times T. Okay, now, similarly, we're going to get something for y of x. Okay, but this is going to be positive for y of t. We're going to get negative b sine A minus B over B times C. And so to represent the parametric curve of this situation where we have a smaller circle rolling clockwise inside of a larger circle, is we are going to add these together, just like we did before. So our final result for our parametric equations, let me do this in orange. Okay. So to represent this situation, we would have x of t is equal to a minus b cosine t plus b times cosine of a minus b over b, oops, not I, t, okay? And then the parametric equation for y, so y of t would equal a minus b sine t minus b sine, and then the angle would be a minus b over b times t. Okay, and so these become the parametric equations that we're going to use to represent this. And now again, this is just an example. Now here's where the period comes in. So we're going to look at the period of this. Now what's the period? So here's our equations. So let's look at what's going on here. Okay, so the period of this is going to be 2 pi divided by 1 over, A minus B over B. Okay, so that's just using the definition of a period. Okay. Okay, and so if we simplify this, right, so this just becomes what? We just multiply by the reciprocal of the bottom, and so this gives us 2 pi b over a minus b. So this becomes the period of the curve. Okay, or the second function rather. Okay, so again, notice that this here, looking at the angle here, so the period of this, of both of these is this. Okay, and that's describes the rotation here. Okay, so depending on the size of the circle, right? So again, the period of this smaller circle is given by this formula, which is the second piece of the parametric equations. Okay, and so what does that tell us? Well, we can use this to tell us how many cusps there are going to be, because we can take the ratio of A and B. Okay, so the ratio A over B is related to the number of cusps on the graph. Now, what are the cusps? The cusps represent these points, right? So a cusp is where the pinches, right? The points are. So this, for example, in this example, there's 4 cusps. Okay, now I didn't give any values, but again, I'm just using this as an example, a general example. So depending on the ratio A to B, right? So the ratio A over B tells you the number of cusps there will be. Okay, for example, if A is 4 and B is 1, right? If A is 4 and B is 1, then that would tell you there are 4 cusps. Okay, for example, in this case, there are 4 cusps. Okay, so again, the ratio of the bigger radius, right, the larger circle, the outside circle, to the inside circle, right, this one. So if the ratio of those two radii is going to tell you how many cusps there are. Okay, and let's see, is there anything else I want to say about this? Okay. Yes, there is. Okay, so here, a couple of things just to keep in mind, again, as far as behavior goes. This ratio is going to tell you the number of cusps there are if it's rational. Okay, if the ratio A to B is rational. Okay? So if it's rational, you're going to get where the pattern is going to be interesting. You can get some really interesting patterns with this, and it'll tell you how many cusps there are, and eventually, if it's rational, it'll repeat itself. Okay? But what if the ratio is irrational? Well, what happens is then there will be no repeated pattern. So it'll keep moving over for infinity. In fact, we call those space filling, which means eventually it'll fill in the entire space, okay, if it keeps rotating for infinity. So there's an infinite number of cusps, and so they never return to the starting point and are examples of what we call space-filling curves, okay? And so here are some examples. Let me see if there's some examples. Okay, here we go. Okay, here. So here's some examples of some possibilities, okay? So again, these are giving you some possibilities of different ratios, okay, for A to B. Okay, so notice if the ratio is 3, you get 3 cusps. If the ratio is 4, you get 4 cusps, like the one that we see in our general example, and then 5 cusps, okay? And then here we have some other things. So notice how we have some different shapes right here, okay? So different types of stars. But then here, notice that we get other types of stars. And here we get what? We have some rational numbers, but they're not whole numbers. So here we have integer or whole values, right? Whole numbers, and we get things like this. If we have something that's rational, but it's not a whole number, like in these cases here, we get something that looks like this. But notice that they all have repeated values, right? So this keeps repeating itself over and over again, right? But what if you get something that's irrational, like in these examples? Okay, so what if you get pi? What if the ratio is the square root of 2, right? Both of these are irrational values. Then you get something that looks like this, which is what we call the space-filling pattern. And look at the nice pattern that you get. So look at this one. I like this one's cool. So these are the type of things that you can get with those spiral graph things that you can get for your kids. But it's all based on this idea of parametric curves. Okay? Okay, so that's it on hypocycloids. But again, the main thing is these are the parametric equations that describe this situation. And again, remember that this is the period, okay, for this, right? This is the period, and then the ratio of A to B, right? The outside radius divided by the inside radius, the bigger radius divided by the smaller radius, it tells you the number of cusps if it's rational. If it's irrational, then you have an infinite number of cusps, and that's where you get the space-filling curve. And again, just make sure you practice these, okay? Do some examples, right? So for example, let's see, I have one. So here. So for example, this one might give you something like this, right? So if I have parametric equations that are x of t equal to 3 cosine t plus cosine 3t, and then y of t equals 3 sine t minus, that's right, minus sine 3t, okay? And so notice that again, in this case, what's the period, right? So remember the period? The period equals what? It's going to be 2 pi times b over a minus b, right? So in this case, what's a and b? Well, in this case, the ratio is 3, right? The ratio is 3, which which again fits this. So what could that be? Well, 3 over 1, right? So this is a minus b, over b. Well, b is 1. Well, that means you've got what? 4 minus 1 over 1. So that means a is 4, b is 1. So you can easily figure this out. And so that tells us, 1, the ratio is what? 4 over 1. So there are 4 cusps. Now what's the period? The period is 2 pi what? Times b over a minus b, which is the reciprocal of this. Right? So it's going to be 1 over 3. So guess what? The period is 2 pi over 3. Okay? So the period is 2 pi over 3. The ratio of a to b is 4, so that tells us there's 4 cusps. Okay. I think that's it. See you next time.